So, welcome to this dissertation of Adam Lycksam with the title From Concepts to Conditions, Bridging the Gap in AI-based Maintenance Systems. And we have, apart from the respondent, Adam, we have an opponent that we're happy to welcome, Holger Fröning from Heidelberg University. So welcome. Then we have a grading committee consisting of Johan Lilius from Åbo Academy in Finland, and Niklas Björsell from the University of Gävle. And finally, we have from Sweden University, Stefan Lindström. So, the procedure of this dissertation is as follows. Adam will present his work, a summary of it, and when this is finished, we will have a short pause, around 10 minutes, so we can remove the YouTube equipment. So after this, the floor is open for the opponent, Professor Fröning. So he will lead the discussion with Adam. And when this is finished, we move on to the grading committee to ask their questions. And finally, the floor is open for the audience, both online and here, to ask questions. And when everything is finished here, the grading committee will have a meeting taking the decision. And then the audience can move to the S building and wait for the decision, and there will be cake there also served. And we, at least we that are here in physical form, will join there. So Stefan and me. We will try also to connect the rest of the grading committee and the opponent into the S building when the decision is made. So then we come to your presentation, and the first question is also if you have found something that we will add or correct in the thesis.
I'd like to add that at the sixth paper, since the thesis was printed, actually has been published. So I'd like to add that with minor edits.
Yeah, good. So, you're welcome.
Thank you so much, Matthias. You know, as an industrial PhD student at SCA for the past couple of years, I think I've had major opportunities to develop state-of-the-art methods, but also to test these in a real industrial environment. And from the start, my goal has been to be a part of a transformation of how maintenance is conducted with the assistance of AI. So the aim of this work has been to develop methods that actually work on a general basis in industrial applications, but also to reduce the gap between the scenarios that are being defined in research and those that occur in practice. And that is what this thesis is all about. And it's also what this presentation will be all about. Now let me start by introducing you all to the underlying problem that this research targets. I'd like to show you this figure. Now, to me, this figure symbolizes an industrial environment. So what I see here, I see a bunch of different machines consisting of different components in a complex manner, working together in a manufacturing process, right? Now, the issue is that these components, they degrade over time. So eventually they will fail if it doesn't do anything about it. So what happens if they do fail? Well, firstly, if we run equipment to failure, the cost is high, the maintenance cost is high, because we might need to replace the whole machine, right? But even more so, consider that we remove one of the machines from this manufacturing process. The risk is that we can't produce anything. So we get something called unplanned downtime. And the cost of not being able to produce anything can be extreme. So naturally, you know, industries, they have different types of strategies to handle this issue, to prevent failures and unplanned downtime happening. And advancements in technology, you know, availability of sensor data that describes the health states of these components and machines, as well as, of course, you know, improvements to AI algorithms, has led to extensive research in data-driven and particularly deep learning-based methods. And it has been shown that these types of methods are able to find complex patterns in the data and relate those to different fault scenarios in these machines. But the issue is that, considering that we want to deploy these on a general basis in practice, it's much different from showing that it's possible to find faults in equipment. Many challenges exist to succeed in practice. So if we look at the literature in this area, we'll find many different challenges from a practical perspective. This thesis targets 3 challenges. And the reason why these 3 challenges are targeted is because they are fundamental in order for us to be able to deploy these methods in practice. So the first challenge is that if we look locally on a single component in one machine, very often we don't have any historical events of failures or faults, because a single component can easily last for 5 to 10 years without failure. So if we look globally, then yes, we frequently have failures, faults, but locally we can't expect to have any historical labeled data that describes fault scenarios. And actually this challenge, I don't think, would have been such a major challenge if it weren't for the other challenge. So the first and second are deeply connected. And that's the discrepancies in the sensor data between machines. So if, for example, consider vibration data, which is one of the, if not the most common type of sensor data used to monitor mechanical equipment, we see that if we look at the data extracted from 2 different machines, we'll see that the data is quite different because of noise, because of load, rotational speed, etc. Meaning that even if we develop one model for one machine, doesn't necessarily mean that it will work for another. So these 2 challenges makes it very difficult to deploy deep learning-based methods in practice. So the last challenge is that we need to consider these machines as systems, right? They consist of multiple different components, and as a when we try to make maintenance decisions, it's important to know what is the cause of a fault in the machine. So we need to be able to separate these different fault scenarios in practice. So if we consider the different research areas in predictive maintenance in the context of deep learning, we'll find we can sort of group them into these different areas. So the first area is anomaly detection. So the basic idea here is generally that try to learn from the healthy state of these machines, and use multiple different sensors, so-called multivariate anomaly detections. So we don't really need any historical faults, So we learn from the healthy data, and by understanding the behavior of a healthy machine, we can then separate abnormal events from normal in an online scenario. And basically, what we have is we have a model. We have an anomaly score method that defines how anomalous a point in time is, and we have a threshold. So in current research, the most commonly aspects that are evaluated is the scoring method and the model. So what often is like not evaluated is how the thresholds are set. And that's fine in like if you want to just, for example, find the best anomaly detection model, but in practice, the determination of these thresholds is crucial. So currently, it's quite unclear what kind of procedure we should use to set these thresholds in practice, so that the method as a whole is accurate and robust. The second area is fault diagnosis. So in contrast to fault diagnosis, here we use labels. So the issue with anomaly detection, as you will see, is that it's difficult to separate between faults in machines and anomalies that are just abnormal, for example, production settings that affects the data. But here we try to say exactly what is the fault in the machine. But of course, I mean, as I said, we have these challenges that we need to handle. So a rather prominent approach when we try to use fault diagnosis is something called transfer learning. So in transfer learning techniques, the main idea is that try to learn from labeled sources. You can think about, for example, a laboratory environment where it's easy to collect data with high quality. We try to transfer that knowledge into, for example, an industrial environment. But the issue with state-of-the-art research is that at least once, or in most studies, most of the challenges that are being defined, challenge 1 to 3, are disregarded. So for example, assuming that label data is available from the target machine, or that the deployment of the model is on the same machine as the training data. In practice, of course, we need to be able to deploy the model on a completely new machine. Otherwise, it's very difficult to create, solutions that work on a general basis. So there need to be more methods that target these scenarios and are what is called for domainization. And a domain in this context means a machine with a unique operational condition. The last area is remain useful life. And this is extremely valuable if we succeed, because what we try to do here is actually to tell the user when the component expect to lose its function. So if we have an accurate prediction of this, we can predict maintenance needs and plan maintenance in advance. But in practice, it's quite difficult to develop methods that work on a general basis. And there are many similarities as to fault diagnosis. Here, transfer learning techniques are extremely common for deep learning approaches. But it's unclear how these methods will work in practice, because most studies, they don't evaluate these methods in scenarios that we actually expect to encounter. You also see that it says component fault diagnosis and component remaining useful life prediction. A limitation of highlighted throughout in several reviews is that there is a lack of studies considering that the multi-component fault scenario. So most of these studies only consider one single component in the evaluation of development methods. Of course, in practice, that method also needs to handle scenarios where other types of faults occur as well, and need to be able to separate that from the component that's being targeted for that method. So based on these research gaps, the following research questions were defined. So the first question relating to anomaly detection. How can multivariate anomaly detection method based on deep learning be improved to increase the performance compared to state-of-the-art in industrial applications? Research question 2 for fault diagnosis. How can a deep learning method for domain generalization for bearing fault diagnosis be developed to outperform state-of-the-art methods and demonstrate higher accuracy in data from an industrial environment? In this question, the bearing is targeted, and bearings are one of the, in many studies, show to be the most common component in industrial equipment to fail. That is why it's targeted for the component-specific models. But of course, other faults are also evaluated throughout this work. The last question is related to handling all the challenges together. So how can state-of-the-art multi-component predictive maintenance system for rotating machines be achieved? So if we look briefly at the methodology, we realized quite early that these research questions were quite difficult to answer with a single paper. So for all questions, knowledge were gained from one paper, making it possible to answer the research question in a succeeding paper. So both methods and knowledge were, extracted. And you can also see that the research question 3 is sort of a aggregation of all the knowledge gained throughout the process. So if we started looking at research question 1, where there are 2 papers published, we'll briefly describe some of the knowledge gained from the first paper. So as I talked about earlier, in multivariate anomaly detection, there's different parts of a method. We have the model, we have a scoring method, and we have the threshold setting procedure. And all of these are important to create a robust and accurate system. So in this study, a new type of scoring method was suggested, that were also used in the second paper, and showed higher accuracy than the other approaches, as you can see here. The higher value means higher accuracy. So in the second paper, this method was used, and the second paper was targeting research question 1. So the idea here is to create a new type of procedure to generate optimal thresholds for these multivariate anomaly detection methods. And the idea was to use expertise of a user. So instead of using complex automated threshold setting procedures where we also have to set certain parameters, we use the user instead. So the procedure starts with us setting some initial thresholds, and also clustering anomaly segments together based on certain characteristics in these anomaly segments. So that's the initiation of the procedure, and then we iteratively interact with a user that gives us some information about cluster segments shown. And the goal with the whole idea with this whole procedure is to minimize the number of interaction with the user without losing valuable information that the user has to give us in order to optimize these thresholds. So when this procedure is terminated, we're able to set thresholds that are quite optimal and deploy this method in practice. So if we look some of the aggregated some of the results from this study, we can see that UBT, as you can see, the red bar, is the suggested approach, and the other are state-of-the-art automated threshold setting procedures. And as you can see here, the higher value means higher accuracy. We can see that the suggested approach gives us higher accuracy compared to the automated thresholds in this experiment. Of course, we also need to consider the number of interactions with the user. And we can see that quite few on average was used, but still there's interaction needed, which can be argued to be I mean, acceptable given the much higher accuracy and performance. So if we summarize some of the key aspects for research question 1, I think it demonstrated the value of using, well, firstly, the separated anomaly scoring method that was suggested in paper 1, but also to use the expertise of the user when setting these thresholds in practice. But another, I think, important insight from these studies was that it's quite difficult to set thresholds to get good methods in practice, and there's still a risk that we have a lot of false alarms, which is extremely problematic in practice. So it's quite difficult to rely solely on, anomaly detection methods in practice. Moving over to research question 2, where also 2 papers were published. Briefly about paper 3. So the idea here was to extract data from SA, meaning a real industrial environment of bearing faults and also another fault scenario, and to make this data set available for in this thesis, but also for other studies to be able to evaluate their methods on actual data from an industrial environment and actual scenarios. And in addition to that, a paper was published that described the characteristics of this data so that future studies can understand the requirements needed for these methods when they develop them for practical scenarios. So some of the key, basically the study confirmed challenges 1 to 3, and some of the interesting aspect was high discrepancy. You can see an example here in the figure showing the difference in we can say the amplitude vibration signal between the different scenarios. That historical faults are quite rare, and also, of course, the occurrence of multiple fault scenarios. So with that knowledge and also the availability of a data set where we can actually evaluate a method for a targeting a real industrial scenario, a method was developed for research question 2 in paper 4. And the whole idea here is to use vibration data to create a method that you can deploy on any new machine without needing any historical examples of fault from the machine. So basically creating a method that you can deploy on a general basis in industrial applications. So let me tell you some of the key aspects of this method. Start off with using multiple different sources for the data. And this means data from multiple different machines with different operational settings. Because of the availability and high quality data from a laboratory environment, which is available. And one of the key aspects is a knowledge enrichment procedure. So instead of using, which is common, using the AI algorithm to learn from scratch, basically, to learn to connect patterns in the data to these different fault scenarios, try to enrich knowledge that we have about the characteristics of bearing faults in this case in the data to make it easier for the algorithms to learn what actually constitutes a fault. Make sure it doesn't learn, for example, random events in the data and think that that's related to faults. So to create a more robust and accurate method, basically, or model, sorry. In the model development, it's also targeted the features from the knowledge enrichment standardization procedure. And also a transfer learning technique was also employed to further decrease the discrepancies between the domains during training. And the last aspect of this approach is to use a time-based contextual enrichment, meaning that instead of using one single extract of a vibration measurement that could possibly contain randomness, making the model inaccurately predict a fault, we use a context of several different extracts in the final predictions to increase the robustness and reduce the number of false alarms, or that was the idea. So if we look at some of the key results, you can see that there's 3 cases. I think in total, I think it was 27 different tasks that this method was evaluated, considering the scenarios expected in practice, so transferring between machine, for example. We can see that on the first 2 cases, the performance were better than the best compared state-of-the-art methods. And case 3 was the SCA bearing dataset, where we had no, there were no prior publications that we can compare with, but the accuracy there was also really high. Interestingly, if we look at the ablation study, we can see that the most important aspect for the performance of the model was the standardization, meaning the knowledge enrichment procedure. That was the most important part of creating the high accuracy for the method. Of course, we can also see that the metric learning, the transfer learning technique was also, of course, important for the high accuracy of the method. So if we summarize briefly on research question 2, what was demonstrated in this study was the value of using prior knowledge, incorporating that into the method development, but of course also using transfer learning techniques to create methods for domain generalization of component mechanical components using vibration data. So to the last research question, 2 papers were also published. In the first paper, methodologies for transfer learning techniques used in state-of-the-art research were evaluated. And the reason why I evaluated that was because there is a lack of, as I said before, lack of evaluation on scenarios expected in practice. And the knowledge needed here was to know which methods are suitable for this bigger picture. If we want to deploy this in practice on a predictive maintenance system, what type of approach should we use for predicting the remaining useful life of components? And interestingly, we can see here, for example, if we consider the scenarios, most of the scenarios evaluated in current state-of-the-art research, you can see the figure to the left, we can see that the implemented method were able to quite accurately predict the remaining useful life. You can see that the ground truth is the red line, the degradation of in this case, the bearing. So quite accurately, actually. But when we consider other scenarios that we also expect to actually expect to occur in practice, we see that the performance was really poor. So the key aspect I think was learned from this conference paper was that it's quite challenging, in general, to develop general methods for remaining useful life predictions, and that the current methodologies it's difficult to make them work in practice. There was also find that can be of great importance to also consider diagnosis in these methods, especially if you consider the occurrence of multiple faults from different components. So based on all the knowledge and methods developed throughout the previous paper, a hybrid framework based on vibration data was developed, targeting research question 3. So what do I mean by hybrid? Well, you can see that there's multiple different types of methods in this framework. You have component-specific models at top for diagnosis and remaining useful life predictions, and those are specifically designed to capture one fault in one component and declare everything else healthy. So it's specifically designed for that component. So it becomes very good at handling faults and understanding faults there. The other part is general anomaly detection, which is used to validate the component-specific diagnosis, making sure that we have less false alarms. It's also used in scenarios we don't have a component-specific model. So what I mean is that we can actually deploy a system based on this framework without having a component-specific model for all the components in the machine. We can still deploy it. It's better to have a component-specific model for all the components, but we can still deploy it and get valuable insights. So to evaluate this framework, an instance was implemented and compared against some alternative approaches to this big challenge, targeting all the challenges 1 to 3. Evaluated in multiple different scenarios, considering transfer between different machines, and deployment on different machines, also multiple different fault scenarios from different components, etc. So what we were able to see that the proposed implemented instance was able to outperform the alternative approaches on almost all metrics. You can see, for example, considering false alarm, the proposed methods were able to have 0 false alarms, while the other approaches were often, in most scenarios, gave quite a significant amount of false alarm to the user. The only metric where we the implemented approach were slightly worse, was for the late prediction. So it had a slightly later prediction of when the degradation in a component started than the alternative approaches. It had higher accuracy for predicting remaining useful life, and it also correctly classified all the fault scenarios, while the other alternative approaches had several misclassifications. So, for example, when there was a scenario where the true fault was from a misalignment, then in the shaft, then the alternative approaches often in many types identify that as a bearing degradation fault, meaning that the user would get totally incorrect information about what to do, because different types of component fault scenarios might have different maintenance actions. Also, if we consider the robustness, considering different, what you see in top here is different parameters setting the sensitivity of these methods. You can see that the alternative approaches were quite sensitive to setting optimal parameters, while the suggested approach were quite robust, even high accuracy, regardless of what types of parameters were used. So, so the summary for research question 3 was, I think that the results sort of demonstrated the value of using a hybrid framework, using different types of methods. Advantage of each method type together to get a really accurate and robust method that can handle the scenarios that we expect to encounter in practice. So over to some conclusions then. So this thesis has provided methods that has been extensively and rigorously, especially considering suggesting in paper 4 and paper 6, on scenarios expected in practice. And the results indicate that these methods can be used on a general basis in industrial applications. But in addition to that, this thesis also presents insights that can be used to reduce the gap between the scenarios defined in research and those that we encounter in practice. And I think a really good example of that is the paper and dataset published. So we provided a dataset that from the actual industrial environment that can be used for evaluating methods in future work, but also describing characteristics of that data so that future work understands what the requirements are for these methods. And I also want to, I think that the two major insights when developing these methods that I want to really emphasize is the value of utilizing prior knowledge. So instead of just training from scratch, why don't we use the things that we already know and try to incorporate that in a training procedure so that we create more robust and general solutions that have potential to really work well in practice and really generate value. And the other aspects, of course, shown in paper 6 is the potential value of using hybrid approaches. And this is also supported by previous studies that have seen similar results as well. But of course, this thesis also has limitations. And I think even though the goal has also always been to target the scenarios expected in practice, it's still been difficult in the evaluation. I think, for example, a limitation of paper 2, a simulated user was used. Of course, that simulated user will probably not react the same way as a real user, and you might have even more challenges there that you need to consider. And in the industrial dataset published has much lower quality than the datasets available in a laboratory environment, which can also be a challenging factor when you try to evaluate these methods. But then again, it's difficult to expect the same quality in the data in the laboratory environment and in practice, because in practice you have sensors that goes down for a period of time. You might not have the same sampling rate, so it might not get the same quality in the extracted measurements either. But I think that's something also we need to expect also. So I think that the biggest limitation, I think, which would have been extremely valuable, would have been to incorporate more component-specific models. So in evaluation, multiple different faults from different components were considered, but only one component-specific model were developed. So I think it would have been better if more component-specific models were developed. But I guess that's left to future work. So if we talk a bit about future work, I think that there's a need for a shift in current research towards scenarios that are expected to occur actually in practice. And one of the aspects is changing the way we evaluate methods. And the thesis gives some suggestions that targets the challenge 1 to 3, how future work can evaluate their methods, increasing the potential that they actually work in practice, and not evaluating scenarios that only work in, for example, a laboratory environment. The other, of course, also related to that is, several reviews in this area has highlighted that there is a lack of studies considering multi-component fault scenarios, as I said. So more research needs to consider the scenarios where multiple component fails and the management of that. The paper 6 has shown in line with previous work the value of using hybrid methods. So future research should explore that further. Explainability of methods. I realized even by my work at SA that it's not necessarily enough to have a method that a model that you actually show is really good in practice. you also need to consider interaction with the user. So will the user understand what to do when the model has a prediction? Will the user trust that the model makes the correct determination? Because if it doesn't trust the prediction, the risk is that it's just standing there and no one uses it. So I think that explainability will be crucial in future work. And obviously, when considering deep learning approaches, then of course, explainability AI be of great value in future work. And the last thing I want to say is that we need to consider that it's not only discrepancy between machines, but we also need to consider that the machine that we're monitoring change over time. It might be that we change sensor on the machine, affecting the data. It might be that we make some adjustments, changing some of the components, or changing the production line. And all that can affect the data. So there needs to be procedure methods to handle degradation of the performance of these models in practice, so that you can adjust them over time, making sure that they're not just accurate when we deploy them, but also accurate in the future. That was all I had to say. Thank you so much.
So, thank you, Adam. We will now have a short pause, 10 minutes, and we'll be back in 10 minutes, and then we will start the discussion of the thesis.
Det var längre när jag körde liksom. Tack så mycket. Tack.
Du får sluta dela.